Hello everyone, my name is Chiberu Patrick Mwanguzi and I have come to take you through this tutorial on thermodynamics and chemical reaction kinetics. First and foremost, we are going to look at the definition of thermodynamics and it will help us understand what we are going to be studying. Thermodynamics is the study of the flow of heat or any other form of energy into or out of a system as it undergoes a physical or chemical transformation. So by looking at this definition, we are looking at the study of the flow of heat. Yes, we know what heat means. Heat transfer, that form of energy, which occurs as a result of temperature difference between one part of the object to another part of an object. Yeah, or any other form of energy. So other forms of energy, we have many, such as sound and light. Then, as it goes into or out of a system, we shall look at the definition of a system. A system is any part of the universe under thermodynamic study. And we have other key terms like undergoing a physical or chemical transformation. A physical transformation, this can be maybe melting or boiling, but chemical transformation can be something that is irreversible. Talk about rusting, talk about burning, those are kinds of chemical transformations. So we go ahead and say, we consider certain properties of a system such as temperature, pressure, volume, and concentration. These properties should not be underestimated when we are looking at thermodynamics, because actually it's due to these properties that we study thermodynamics. Measuring changes in these properties from the initial to the final states provides information concerning changes in energy and related quantities such as heat and work. So it's due to these properties that we have mentioned, temperature, pressure, volume, and concentration, plus a few others that we shall see, that when we measure their initial and the final changes, we can be able to tell the quantities, maybe of heat and work done. Okay, let's continue. We have the types of thermodynamics. We have the classical and the statistical thermodynamics. So, when we talk about classical thermodynamics, what do we mean? Classical thermodynamics concerns the relationship between bulk properties of matter. So here we want to look at matter at the atomic or molecular level. We won't look at the protons, the electrons, no. We will look at matter. If it's a cup, we look at it as a cup, not looking at the components, those small components that make up the cup. No, we look at the cup itself. We have that statistical thermodynamics. This one seeks to explain those bulk properties in terms of constituent atoms. But however much they're saying in terms of constituent atoms, it doesn't mean that they're going to look at each individual atom. No, they're going to look at this collection of atoms, or what they're calling aggregation of atoms, combination of these atoms. So it's a group, but not studying individual atoms, because thermodynamics deals with bulk properties, so we need something large to increase our area of study, and that is the statistical thermodynamics. So, scope of thermodynamics. What is under thermodynamics? What shall we look at? What has been discovered? You realize that it's under thermodynamics that important laws have been derived. Those laws include the Van Hoff's law of vapor pressure, we have the phase rule, and the distribution law. All these can be derived from the laws of thermodynamics. The laws of thermodynamics, we have three, which we shall look at in our coming tutorials. So, it's under also thermodynamics that we tell whether a particular physical or chemical change can occur under a given set of conditions. Conditions such as temperature, pressure, and concentration. So, thermodynamics also helps us in predicting how far a physical or chemical change can proceed until equilibrium conditions are established. Because just imagine heat is flowing from point A to point B. It's going to flow until there is that equilibrium between the 2 points. And after it has reached equilibrium, we can now tell that heat, maybe the initial temperature was this, the final temperature was this, then at equilibrium this was established. So there are some limitations of thermodynamics. So there are some criticisms. So thermodynamics, it only applies to microscopic systems consisting of matter in bulk, like we saw in the types of thermodynamics. We have the classical and the statistical. So it only deals with macroscopic, something in bulk, but not something which is microscopic, such as atoms and molecules. No. So it's only applicable to macroscopic systems consisting of matter in bulk. Next, it ignores the internal structure of atoms and molecules. Still, we saw that under the types. It doesn't look at the protons, the neutrons, because it deals with matter in bulk. So it will ignore the internal structure of atoms and molecules. It does not bother about the time factor. So it ignores anything regarding the rate of a physical change of a chemical reaction. There is nothing about rate or time taken for this and this change to occur. No, in thermodynamics, we look at only the factors. The factors we have given: pressure, volume, concentration, and temperature. There is nothing like time, so it does not bother about the time factor. It is concerned only with the initial and the final states of a system. It doesn't consider the stage in between there. It only considers what was the initial temperature and what is the final. What is the temperature change is final minus initial to get the temperature change. So some key terms we heard about system. So what is a system? A system is that part of the universe which is under thermodynamic study. When I am talking about a vacuum flask, there is that interior part of the flask which keeps the maybe hot water hot. Then there is that glass, and then there is the outside. So if I'm making a study, the system will be that interior that keeps the hot water hot. The surrounding will be that glass that separates that, maybe in physics we can call it a vacuum. Yeah, that space that separates the glass and then the outside plastic bit of it. That will be the surrounding. Sorry, that will be the boundary. So the surrounding is anything that is outside the system. So that plastic bit of it and anything outside our area of study will be the surrounding. Yeah, so we can put it into definition and say system is part of the universe which is under thermodynamic study. Then surrounding is any part of the universe which is not the system. Boundary, this is a real or imaginary surface separating the system from the surroundings. Another example we can give, we can look at our planet. If we are studying our planet will be the system. Then if we look at other galaxies other than our planet, but we are still studying our planet, those galaxies will be the surrounding. And what separates the other galaxies from our planet will be the boundary. So if it's just space, that space will be our boundary. So types of thermodynamic systems. We have the homogeneous system. In a homogeneous system, there is always a single phase. It is uniform throughout. There is no separation between the phases. Take an example of, it is more like in chemistry where you have miscible liquids which has only one layer. So it's more like miscible liquids. It has only one single phase. For a heterogeneous system, it consists of 2 or more phases. So types of systems, we have 3 types of systems. We have an open system, so this is where the boundary is open and uninsulated. That means it can transfer both matter and energy across the boundary. We understand that. So for an open system, just imagine a flask is just open. That means both matter, the content inside, and energy can easily flow out of that flask. And so it's an open system. A closed system, the boundary is sealed but not insulated. That means energy can move out, but matter won't cross. So for that case, maybe a flask that has no vacuum in it, you'll find that there is heat that will flow out, but probably the content in that flask won't flow out. So that's kind of a closed system. An isolated system, the boundary is sealed and insulated. So here it's like we have a perfect flask, a perfect vacuum flask, where there is no escape of energy and there is no escape of matter. So there is no interaction between the system and the surrounding. So I was taking you back to miscible liquids to explain homogeneous and heterogeneous system. For a homogeneous system, it's more of a miscible liquid, like we are seeing in this part of the video. We have potassium nitrate. When it's alone in this conical flask, we shall say it's a homogeneous system. But when you add something like lead to iodide and then potassium nitrate and they form two different layers, it will be a heterogeneous system because there are two different layers. When we come to the types of systems, we have what we call an open system. An open system, we said both matter and energy can cross the boundary. For a closed system, only energy will cross, but matter won't cross. And then for an isolated we have nothing can cross, not matter, not energy. So no interaction between the system and the surrounding. Systems in which no thermal energy passes into or out of the system are said to be adiabatic systems. Take note of that. So we have properties of a system. We have the intensive property. So what do we mean when we say intensive property? This property, these properties do not depend on the quantity of matter present in a system. What do we mean? Let's give some examples. We have pressure, temperature, density. When you look at the density of water, the density of water in a glass is 1 gram per cubic centimeter. But that water, even if it's water in a sea, it still remains 1 gram per cubic centimeter. So it doesn't change whether the quantity of water changes or what. When the boiling point of water is at sea level is 100 degrees Celsius. But the boiling point of water at sea level in an ocean is still 100. So these properties don't change no matter how much you change the quantities of matter. So those are some of the examples. And here they're giving us, if the temperature of a glass of water is 20 degrees, then a drop of water in that glass has a temperature of 20 degrees. And if the concentration of salt in a glass of water is 0.1 molar, then any drop of water from the glass also has a salt concentration of 0.1 molar. So concentration is an intensive property. These properties do not depend on the quantity of matter present. So we have pressure, temperature, density, concentration, and so on. When we look at the extensive properties, this is the opposite of intensive. These ones depend on the quantity of matter present in the system. So examples, we have volume. So when you put 1 centimeter cubed of water in a glass and another glass you put 20 centimeters cubed, you realize the volume has changed. Number of moles enthalpy, entropy, Gibbs free energy. All these are extensive properties. They depend on the quantity of matter present in a system. So we have a table which is trying to exhaust all, giving us more of the intensive and extensive properties. On the intensive, we had given temperature, pressure, density, concentration, we have boiling point, surface tension, refractive index, viscosity, freezing point. All these don't change. And then the extensive, we have mass, we have the volume, internal energy, enthalpy, entropy, and Gibbs free energy. So you can read through and you can add more to the list. But you find that most of the energies, like enthalpy, entropy, internal energy, Gibbs free energy, those ones fall under the extensive because they always depend on the quantity of matter in a system. Yeah. States of a system. A thermodynamic system is said to be in a certain state when all its properties are fixed. Remember what we said, the properties are, we have pressure, temperature, volume, and maybe concentration. So, if a certain property is fixed, we can say a thermodynamic system is in a certain state. The fundamental properties that determine the state of a system are pressure, temperature, volume, mass, and composition. These are referred to as state variables or state functions or thermodynamic parameters. So in case you're given any, it means the same. State variables, state functions, or thermodynamic parameters all refer to the same thing. A change of any system from the initial state to the final will be accompanied by a change in state variables. This is what we said about thermodynamics. It deals with the initial and the final states. So any change of a system from the initial to the final, there will be a change in the state because there will be a change maybe in pressure, maybe in temperature, or volume. It is not necessary to state all the state properties to define a system completely. The remaining state variables, pressure, volume, temperature, are interrelated in the form, we have that formula, that's pressure times volume is equal to our constant R and then temperature. So if pressure and temperature are specified, then the third variable of volume is fixed automatically and can be calculated since R is a constant. The variable P and T, which must be specified to define the state of the system, are called independent state variables. The remaining state variable, V, which depends on the value of P and T, is called the dependent state variable. That's in case you're looking for volume and you've been given pressure and temperature. So the dependent variable will be volume. When the state of a system is altered, the change in the variable depends on the initial and final states of a system. So that will be changing maybe in temperature, it will be the final temperature minus the initial temperature. The way in which the temperature change is brought about has no effect on the result. So what the cause of the temperature change has no effect. So some changes of states. If a state function x maybe depends on other state functions, say a, b, and c, then the changes in x resulting from simultaneous or consecutive changes in a, b, and c can be represented by a complete differential as follows. Let's see. So this is dx, maybe change in x, is equals to dx over dA given b and c, dA, then plus dx, that's db, then ac, then db plus These are changes, change in x over dc and then ab dc. But we shall look at that in the later calculations. Let's look at equilibrium and non-equilibrium states. A system in which the state variables have constant values throughout is in a state of thermodynamic equilibrium. So, what is thermodynamic equilibrium? This is when a system in which the state variables have constant values. So, that will be a system in a state of thermodynamic equilibrium. A gas confined in a cylinder that has a frictionless piston is in equilibrium state. If the gas is compressed by moving down the piston, P and T change and the system loses the equilibrium state. Remember, for a system to be in equilibrium, the state variables have constant values. So if P and T, the values change, then the system loses equilibrium. So thermodynamics is only concerned with equilibrium states. The criteria for equilibrium. The temperature of a system must be uniform and must be the same as that of the surrounding. That's one. The mechanical properties must be uniform throughout the system. That's mechanical equilibrium. Where the point before, that is for thermal equilibrium, whereby the temperature of the system must be uniform and must be the same as that of the surrounding. And for the mechanical properties being uniform throughout the system, that's mechanical equilibrium. No mechanical work is done by one part of a system on any other part of the system. So for chemical equilibrium, the chemical composition of the system must be uniform. That means there is no chemical change. For a chemical equilibrium, the reaction does not appreciably change with time. Then perturbation of such equilibrium shall result into return to equilibrium, like any change of such equilibrium. A thermodynamic equilibrium can be stable equilibrium. Stable, the system is at its lowest possible energy level. That means there is no change, like it's stable actually, yeah, like it's saying stable equilibrium, the system is thermodynamically stable. Metastable equilibrium, the system is at a lower energy level, but not the lowest possible. For we can give an example, a mango on the top of a tree, then a mango falling, but halfway, it's halfway between the tree and on the ground, then a mango which has actually reached the ground. So the mango on top of a tree is in a state of unstable equilibrium because it's at a higher energy level. Then metastable when it's halfway between the tree, top of a tree and the ground, then it will attain stable equilibrium when it finally hits the ground. So we can take an example of that picture. We see the metastable equilibrium. When it's at a higher energy level, it's unstable. That's why it comes here still, it's still unstable because it's at a higher energy level. Then finally it attains stability when it reaches down. Okay, so thank you for watching. I guess in our next tutorial we shall be looking at thermodynamic processes. I didn't want to make this video so long, and hoping you subscribe, hoping you like, you share and comment. Thank you very much. I remain Patrick Chiberu Mwanguzi. Have a nice time. Thank you very much.